Greetings and welcome, friends. Today, we're talking about roots of real numbers. And you might be like, wait a minute, real numbers? What? What are you talking about, Mr. Waddy? Real numbers? Are you telling me, like, couldn't we just say numbers? Are you telling me that there's numbers that aren't real? And maybe I am, subtly implying that. But not so subtly that I'm pronouncing the B in the word subtle.
Real numbers.
So someday there will be non-real numbers. But ignoring that for now, today we're talking about roots. So starting off, let's talk about a square root. It says a square root for any real numbers a and b. If a squared equals b, then a is a square root of b. All right, so that makes sense. That makes sense. Good stuff. So let's do a little example of this. Example. All the way, example. So let's evaluate what is the square root of 9. So notice this cool little square root symbol. That's a radical sign, you can call it. So the square root of 9 asks us a question. Do you know what question that's asking us?
It says, what is 9 squared, which is 49?
No?
Saying what times what is 9. So what times itself is 9.
Yeah, what times itself is 9. Actually, we'll even write that down. This is asking the question, what number multiplied by itself is 9?
What? I have my hand raised.
All right, so that's the question that it's asking us, right? And when thinking about this definition of it, I'm thinking of what squared is equal to 9, right? So what would go here? And I think I've heard a couple people mention it already. The answer is 3, correct, bam. So that means that the square root of 9 is equal to 3. And it's true because 3 squared equals 9, right? By definition, right? Bam.
Boom.
So that's not too crazy, right? No, not bad at all. No es más mal. Bugga bugga is right. So let's do another one. What about the square root of 121? What question does that ask us?
What number multiplied by itself is 121?
Correct. And what number do you think that would be? 11, because 11 squared is equal to 121, right? So the answer is 11. It's not that bad, right? Right. So that makes sense. All right, let's pick it up a notch. So friendly friends, here, put the food away, friends. Let's follow along here. What about the square root of x squared? So that's asking us the question, what squared is equal to x squared? What would go in the parentheses? It's got to be x, right? And I agree that it's equal to x. Technically, later, tomorrow specifically, we'll talk about some restrictions on this, that it's not technically equal to all values of x, but that's fine for now. You get the idea that the square root of x squared is x. Okay, good. All right, what about this? Let's get ready for mind blown.
What is that 3 doing?
Yeah, what's that 3 doing? It's like, hey, look, a tree fort. And he like climbed up there. It's like, no, Timmy, that's not safe. I'm going to call the fire department. Right? Like, so that 3 is hanging out up there. This is called the cubed root of 8. All right, is how you would read that. The question it is asking, what question do you think that's asking?
What cubed is equal to 8?
Sure, you could ask it that way. What?
What's it 3 doing then? If we're just talking about 8.
Because cubed is 3, Emily.
Oh, I'm so sorry.
All right, so that's the question it's asking. So yeah, Well, let's think about that. What cubed is equal to 8? Is it 2? Yeah, I think so. So the cubed root of 8 must equal 2. Not bad, not bad.
But you don't find like never mind.
I don't mind at all. All right.
No,
But if you have any questions, be sure to ask them. So this cubed root of 8 brings up this concept of the nth root. Nth root.
So,
Root.
like, if that 3 had magically become 4, it'd be nth root, right?
No.
Actually, nth root always reminds me of, I don't know if you guys know, like,
Those ferns.
kind of. There's like this plant in the video games Oblivion and Skyrim called Nirnroot. You know what's up?
Or like
And they
grass you
like
cut through in Pokemon.
they grow a little bit, right? And they actually also go like wow, like they're chimey. Whenever I see nth root, I always think about like Nirnroot, but that's fine. So nth root, it says for any real numbers a and b, and any positive integer n. Okay, all right. So n has to be positive, ladies, gentlemen, please, and it has to be an integer.
So that's a number.
So that's a number that is not a decimal or a fraction sort of thing. All right, at this point. So so if a to the n equals b, so that's the nth power, you could say, then a is a nth root. Should it be n nth root?
Yeah.
I don't know.
No, because n isn't a vowel.
Yeah.
Yeah, but it works sometimes like with H, because it's A-N
Well-
or H, like hour, an hour.
Well, either way, it is an nth root of b. Nth root.
N is an H, so
So let's talk about some nth roots here.
it only works sometimes.
So here's a little example. Ba, 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 da, ba.
I'm a little bit.
So look at, we've got like this little 4 here. And actually, let's label some of what's going on. So this 4, this number here, that's referred to as, let's see, I'll write it in this cool purple color. So the 4 is called the index.
Index.
All right.
So is there always a 0 or sorry, a 1? Like where
Ooh.
it's supposed to go?
We'll talk about that in a moment. Yeah, that's a good question. The 16, guess what? This one's so cool. It's called the radicand. What? How cool is that? And then the entire expression is called a radical, which was not Splinter's favorite word. His was cowabunga, but I believe it was Raphael's favorite word, maybe.
TMNT is so great.
Yeah, TURTLE power. You know what's up? That's what's up. So what this is read as, so if I ask you what this meant, all right, 4th root of 16, that's right. I just read that as the 4th root of 16. So that's not read as, all right, this is what it's not. You wouldn't call that 4 times the square root of 16, because that would be 4 times the square root of 16, and that's not what I'm referring to at all. You wouldn't call it 4 square roots of 16 or anything like that, or 4 roots of 16. No, no, no. It's the 4th root of 16, so 4th root of. All right, is what that would be. So like you could have a 10th root, you could have a googolth root, you could have a millionth root, right? All sorts of stuff like that. So the 4th root of 16 is asking us what question?
It's asking us what to the 4, how many, what 4th is equal to 16?
What 4th is equal to 16?
What's the 4th?
Does anyone know what number would go here?
2.
Yeah, it turns out to be 2. So the 4th root of 16 is equal to 2. Good stuff, good stuff. Now, I don't know if you'd ask this question, or I think, Moro, you were implying it. What is the index on a square root?
It's just 1 because it's invisible. It can't be 0 because then
Yeah, 0th root wouldn't make any sense.
0.
What if you have negatives?
There's no negative.
Would it be
there.
2
gonna say
because
it's 2.
when you put the 3 there, it's cubed. So then if you put a 2 there.
Okay, so when this was a 3, this was a 3. So when this is
It's
a
1, then it just
2,
cancels out the
this
rest
is a
of it.
2. Yeah, it turns out that the index of a square root is a little invisible 2, oddly enough.
It makes sense because you're like you're multiplying the number by itself. So
True.
Yeah, you're
That's
squaring, yeah,
you're squaring.
square
Truth is
rooting.
just that people got lazy.
Well, mathematicians like to be efficiently lazy people, so so yeah, they found, figured out when we should stop writing stuff and just let it be implied. So one might say that 2 is the hobbit in the land of roots, right? Because it's a little invisible, it's like cloaked, it's wearing a ring, it's invisible. Yeah, you know what's up. So 2 is the index of a square root. But just for an interesting thought activity, perhaps, what is the first root of 10?
10.
That would be 10, right? Because that would be asking the question, what to the first is 10? And that would not be a very interesting problem. I think you would agree. Right? Yeah, I think so.
Yeah.
All right, so question then, what would the square root of 10 be? I'll even put the little 2 index there just for funsies.
5?
No.
No, it says 25. 2.5?
No? No?
It doesn't go
It's
in
just square root of 10.
Is it,
It doesn't go in increments.
let's see, 2 squared is 4. What's 3 squared? 3 squared is 9. 4 squared is 16. So it's somewhere between 3 and 4. It's probably closer to 3 than it is to 4 because 10 is closer to 9 than it is to 16. So you're saying like 3.2-ish?
It can't really be 3 point anything though, because it would never equal 10.
Can't.
That's the right decimal.
Well, it turns out your calculator has a way of approximating this. It is going to be an irrational number,
So that
meaning it's going to be an infinitely long non-repeating decimal. But let me show you, here's my calculator. Oh, you can
So
see
is
the
it
camera reflected in it.
It's 3.333 repeat. It's 3.3 repeating because that would be 9.9.
Well, let's actually check that out. 3.33. Oh, I got to turn this on, don't I? But 3.33333. And if I raise that to the second power, you're saying that should equal 10?
9.999, which is it.
No, that's too big.
3.2 is what I said.
Well, it turns out on your calculator you can take square roots. If you notice, there's the little square root icon right here, right above the squared button.
Oh, wait, there's a little thing with the X.
And there's an xth root, which is the same as an nth root. So I'm going to hit second and this button, and it pulls up a little square root symbol with parentheses, and I'm going to do the square root of 10, and I'll close those parentheses because I'm a good doobie. And I hit equals, and I get 3.1.
If you round that up, it's 3.2.
Right, you can't round it up or else it won't equal exactly 10.
Although technically this is rounded off to 8 decimals or whatever it is. But yeah, so that's what I'd end up getting. And so yeah, we'll throw a few decimals in there. So 3.1622 maybe. Something around that. And this, like I said, would be an approximation.
So basically, we have to use our calculators for
Maybe. Now, to verify, if I raise that answer to the second power, what should that equal?
10, exactly.
10. Bam, exactly. So that's how you can do a square root in a calculator. If you want to do a cubed root, all right, what you actually have to do first is you type in the number for the index.
And then you press that button second and then the one right there.
Bam, right there. Yep. So that's 3 is represented as the index here, bless you. So if I wanted to say the cubed root of 64, I would get 4. Why is that true? Because 4
times
cubed,
4 times 4 is 64.
64. You got it. You got it, dude. So, good stuff, good stuff. Now, so that's how you can kind of do some of this in a calculator if you had to. Also, I'm sure your phones have this as well. Sometimes the phone calculator, if you flip your phone sideways into like landscape view,
You can get like all the special features.
yeah, it'll have some like more functions there for your calculator. It'll be great.
What if eyes and ears were replaced?
Oh yeah, we do have it. But it's weird because it only lets us go to the calculator. I feel like.
So sometimes on your phone, you actually have to do the number and then hit the square root. I've seen phones be kind of backwards sometimes.
Oh no, it comes out fine. You just put I put like 3. the square
Oh
root.
boy, negatives.
So let's consider these two examples. These are going to be interesting.
Possible.
Well-
Possible numbers.
Well, let's think about the cubed root of negative 27. What cubed is negative 27?
Okay, so 3 cubed is 27. So I guess you
So that would be the same as negative 3 times negative 3 times negative 3, right?
negative 3 times negative 3 is negative.
Two of those minus signs when multiplying would cancel each other out, but I'd still have one negative left over,
So it's negative 3.
and I'd get negative 27. So yeah, it turns out this is equal to negative 3. Huh.
So that wouldn't work if it was like negative 32 to the 4, would it? Because it would
It has to be odd.
Hmm.
right, the
Doesn't
number,
the index have to be odd?
the index would have to be odd always because the correct also would be make it positive. If you have a negative number inside the
Well, yeah, let's think about this this one here. If I was looking for the square root of negative 4, you could try to say 2, but no, 2 squared is positive 4. You could try to say, oh, maybe it's negative 2, but negative 2 all squared is positive 4. You could say, oh, negative 2 times positive 2, but that's no longer squaring, because those aren't the same number.
That's unsolvable.
So yeah, so this one's just like, no. No, you can't make me do that, right? Like, it doesn't make sense. It's impossible. Impossible, right? Would also be an acceptable answer there. So yeah, it turns out that I think one of you guys summarized it, that for, let's see if I can phrase it right, odd roots of negatives are negative. I think you would agree.
All are solvable.
Or are solvable. Even roots of negatives are lame. I'll just bam.
Odd roots.
Let's see. So I want to talk about the idea of a principal root.
Why are they lame?
Now,
Unsolvable.
it's like, I don't understand what you're asking, is what it's saying, right? Like, what do you mean? There is no number that squares to do that. So this next part, you guys won't have to write down, but I can come back to it later if you want to. But we'll explain what it is. Principal root. So the non-negative root, when there is more than one real root, is a principal root. Principal, yeah. So you don't have to write this part down. I'll come back to it at the end of the video. In the case of an odd index and b is negative, the principal root is negative. So in that example, negative 3 I could refer to as a principal root. But what I want to point out about principal roots is, let me take a look back at one of our earlier problems. When I asked about the square root of 9, isn't it also true that negative 3 squared is 9?
Yeah. Because negative has negative positives.
Yeah, and isn't it also true that negative 11 squared is 121?
Yes, sir.
And isn't it true that if that is true, then by definition, that -3 is a square root of 9. What? So it turns out that you can actually have multiple answers to these sometimes. Although we actually, whenever I ask for the square root of 9, I'm only interested in the non-negative root, which non-negative just means it's not negative, meaning it could be 0 or positive. So I only give the positive outcome there. So that's kind of intriguing. So that's what I'm referring to as principal roots. So let's do some quick examples with that, and then let's see if I can fit this whole concept in here. We've got lots of stuff going on. So, if I wanted to evaluate the square root of 64, I'm only technically interested in the principal root, and I would say that's equal to 4. Nope, 8. Haha. You got me there. If I was interested in the negative square root of 64, then I would say -8 is the answer to that evaluation question. And if I actually want both of the roots, I'll put this little plus or minus sign in there, and I'll get the plus or minus 8. Okay, so if someone asks you what's the square root of 100, you only tell them 10. Okay, and actually the square root symbol originally came from this question. It was from the Greeks, I believe, that originated it. And they would be asking the question, what is the side length of a square whose area is 100?
Just be 25, 25, 25, 25.
That would be perimeter of 100. But a side length of 10, 10 times 10 gives us an area of 100. So square rooting literally originated from squares. And cubed rooting? What do you think cubed rooting asks?
It asks.
Triangle.
Close.
Triangles have 3 sides.
That would be asking the question, what is the side length of a cube whose volume is, say, 8?
2.
And that would be 2 by 2 by 2, because you can imagine that there'd actually be like, there's 4 cubes on this top row and 4 cubes on the bottom row, and that would be 8 altogether. So the cubed root was literally asking that question. So as far as the Greeks were concerned, the square root symbol was only ever going to give us a positive answer. Although algebraically, we realize that negatives do technically make sense. But the Greeks viewed mathematics through the window of geometry, and they were like, what do you mean? Like, what's -8 inches mean? That doesn't make any sense, right? They weren't fans of, the negatives in some cases as a result, because they were thinking about geometry the whole time. So let me show you this little chart. And this table is also found somewhere in your book. I don't have your book out here right now. But it talks about kind of the nature of some of these. Don't write this down right now. We'll just talk about it. So let's see. Real nth roots of b. Okay, so if n is even, all right, so like a square root or a 4th root or a 10th root, and b is positive, then I get 1 positive, 1 negative, right? Just like the square root of 9, I get +3 and -3 as my roots. Okay? Agreed? Yes. However, if b is negative, I have no real roots. No real roots. Why? Because the square root of -4, there's no answer to that question that is satisfactory to us, because those don't end up actually being squares. What about the square root of 0?
It's what times itself is 0? 0 times 0 is 0.
Yeah. What about the 4th root of 0? What would that be? So what times itself 4 times is 0?
0.
Also 0. 100th root of 0? 0. Yeah, so there's only one root in that case, and that root is 0. Now, in the case of odd roots, if I have an odd index, and b is positive, so like the cubed root of 8, we got 2. But here I'm actually making the claim that there's no negative root. Let's see if that makes any sense. There's my Nern root there. So is negative 2 cubed not equal to 8? All right, that'd be negative 2 times negative 2 times negative 2. And 2 of those minus signs would pair up for positives, but then I'd get negative 8. So it turns out for odd indices, I think is how I'd pluralize that, there is no negative root. Okay? And that's what this table here is claiming. So there's no negative root. Interesting fact. And if I have an odd root of a negative number, when b is less than 0, like the cubed root of negative 27, I get one negative root, like negative 3, and there's no positive root. Okay, so the odd roots are somewhat interesting in their behavior. But it turns out cubed root of 0 is still 0. So that's some good stuff. Good stuff. So, all right. I know it's been a lot of math we've been absorbing here, but I've just got like, I think, a couple more little examples. Because we gotta talk about simplifying.
Holy small cheese.
So, if I want to know what the positive and negative square roots of 49x to the 8th are, turns out what we can do is break this into things that would cancel out with a square root. Because I don't know if you realize this, but like the square root of 2 squared is 2, because like the square root and the square cancel each other out. All right, it turns out squaring and square rooting are inverse operations of one another. You could. Yeah, you could use the tree method. So I'm going to rewrite this as the plus or minus square root of, I could think of that as 7 squared, times the square root of, now x to the 8th I could break up into x squared times x squared times x squared times x squared. We will do a more efficient approach in a moment. But right, if I break these all up into perfect squares.
Does it say minus x squared like a bunch of times? Or?
Oh, this is multiply. That was a little multiply dot. And all of these squares and square roots will cancel out. And I'd end up with, what, plus or minus 7. And how many x's do I have being multiplied? 4 of them, so that's the same as x to the 4th. Okay? The other way I could have done this problem is I could have broken this up into the largest perfect squares possible. So the square root of 49, I actually knew that was a perfect square. X to the 8th, all right? Maybe you just happen to know, maybe we could write it this way. X to the 4th all squared. Right? And this square root would cancel out with that square, leaving me x to the 4th behind. All right, so there's sometimes some other ways of thinking of that. So that will show up in kind of this next problem where it's a little bit more interesting.
How do you simplify the rest of that answer?
Well, the square root of 49 is 7, and then the square root of the square canceled out, so that would have been x to the 4th, and the plus or minus was still hanging out. So I'd get the same answer either way. I just wanted to point out you didn't necessarily have to write out all of these square roots, because seriously, mathematicians are efficiently lazy people. We don't want to do all that work. All right, how about this question? So here I'm just interested in the principal root. So the square root of 25, you could probably realize is right, square root of 5 squared, or you know that that's just going to be 5 in a second. I'll just write it as the square root of 25. Square root of x to the 5th. Now, what I'm going to do is I'm going to try to break x to the 5th into powers that have the largest exponent that's divisible by the index. All right, I realized I said a lot. Now, I could break that into x, don't write this one down, x squared times x, right? X squared, and x all multiply to x to the 5th. I think you agree?
Yep.
Right? So that's a legitimate way to doing it. But instead, what if I just broke it down into x to the 4th times x? All right, because 4, I happen to realize, is a perfect square, or type of perfect square, right? X squared is that. And I could just kind of think about it that way.
How come before you did it as
when I did it like this.
Well, I was thinking then you multiply them, but then I realized we were using out of the top of
Yeah, yeah. So square root of 25 is 5. Square root of x to the 4th, does anyone know what that is?
X squared.
It's actually x squared, right? Yeah, because x to the 4th is equal to x squared squared, correct? So therefore x squared must be a square root of x to the 4th. It turns out for square roots, I don't know if you realize this, but the square root of x to the 8th was x to the 4th. The square root of x to the 4th was x squared. All right.
So the square root of x and
If they lost an x there.
Correct. Yeah. In fact, what we would just do is divide our exponent by the index. Right? 4 divided by the little invisible 2 gave me the 2 there. But that'll be kind of for future stuff. You don't have to worry about that just yet.
Wait,
Except for you dropped an x.
Oh, good call. And this part couldn't simplify. So that's still stuck inside of a square root. Sorry, my apologies. Good call, friends. Oh, wow. Let's see. So one last example, and we'll call it a day. We can't do one more? I think we can. We're good. We're good, people. So here we are. The 5th root. What? Now, I don't know if you guys realize this, but 32 is actually a perfect 5th. That's 2 to the 5th is equal to 32. X to the 10th, don't worry about it, Emily. We're worrying about this 5th root right here. What's going on with the 5th root? So x to the 10th is actually a perfect 5th. Okay? You could think about that as x to the 2nd all to the 5th if you wanted. Actually, I didn't have my little index over here, did I? Right? Or you could have just realized the thing of that the 5th root of x to the 10th. I'm just going to divide those exponents. All right? Or the exponent by the index, sorry. And y to the 15th, that's going to be the 5th root of y to the 15th. Or I could have thought about it as y to the what all to the 5th? That would have been y cubed all to the 5th. But I'll just leave it like this because I like the little divide trick better. So the 5th root of 2 to the 5th?
It's 2 to the 5th because it's a perfect 5th.
Yeah. So the 5th root of x to the 10th is x squared. And the 5th root of y to the 15th, what do you think that is?
Y to the 3rd.
Y to the 3rd. I like it. So the idea is, I guess I'll maybe point that out. Divide the exponent by the index. So we're going to spend another day on this stuff tomorrow and discover some other properties of these. But in the meantime, have a great day, Internet friends. Bye-bye.